For the introduction, I'm Weilan Li from Fudan University, and this is work joined with Guozhen Wang and Zhou Xu. And today I'm going to introduce 3 computer programs. The first one is called Adams. It's a program that can compute the E2 page of classical Adams spectral sequences and maps between these E2 pages and also the D2 Adams differentials. And the second program is called SS for spectral sequences. The program can compute the Adams differentials and F extensions for maps F. I mean, you start with a collection of, in the very beginning, it starts a collection of CW spectral maps. And as long as F is in certain cofiber sequences, the SS will try to compute those F extensions automatically. And it can also produce human-readable proofs. And the third program is the plots. The plots is a web page, so it let human to read or what's happening quickly, like in plots, and you can interact and navigate through these plots. And for example, you can also have cofiber sequences. So this is like the long exact sequence. For example, this one is from C2, cofiber of 2. You have bottom cell and top cell, and you just go along the long exact sequence. And you also have maps. There are some maps that are not part of some cofiber sequences, but you are still able to like find the image. So the left-hand side is the TMF, and the right-hand side is the sphere. And we are going from 47 to pi 47 of the sphere to the pi 47 of TMF. And so you have to read from right to left. And this line means that these dots map to that dots in TMF. And you can press the shift key on your keyboard and click, left click with your mouse, and then you can move the ribbon around. Or you can also use your keyboard shift plus arrow key. So the point is that, the point is that that is for human reading all these data. Okay, so they are provided in these 2 links. The first link is the data, the plots. The second link is the proofs. Okay, next I'm going to introduce the first program. It's the Adams. The program Adams basically can compute a lot of X groups. So for example, the E2 page of the classical Adams spectral sequence is this X for sphere. And therefore, it's beneficial if we can have very efficient algorithms to compute all these X groups and also various structures on them. For example, for modules over a sphere, then it's so for the sphere, this is an algebra, and for modules, it's a module over the X for the sphere. So there are a lot of structures on them, and the Adams can compute these structures. Okay, so let me introduce a little bit background. So in computational commutative algebra, so this is a math area, a research area, and they have many applications in algebraic geometry, because in algebraic geometry you have to deal with a lot of commutative algebra with ideals, for example, and we often consider algebra like this, commutative algebra. Then if we have a R homomorphism, so like 2 free R modules, and we have a homomorphism, then we can use the technique in computational commutative algebra to compute the kernel. So in some sense, computing the kernel is essentially computing a map K such that this sequence is exact in the middle. So this is like solving a system of linear equations, but over a commutative ring R. So this is doable. This is some already very developed research area called computational commutative algebra. Okay, so the point is that that we can repeat this, and in the end, so you can compute the kernel of f, and then you compute the kernel of k, and so on. Then we get the resolution for the kernel of the very first map, and that's how. So, for example, if you want to get a presentation for this module M, then it's equivalent to giving a presentation like, so the presentation is basically generates modular relations. So you start with a module like this with presentation, then you, by computational commutative algebra, you can just obtain the minimal resolution. Okay, so the central concept in this area is called Groveland basis and the Bucherberger algorithm. Okay, next. However, many important algebras in algebraic topology, such as the spectral algebra, are not commutative. So one would like to generalize the theory of Groveland basis and also many algorithms in this area, so that we can apply all these new theorems and algorithms to non-commutative algebras, including the spectral algebra. So we would like very much to have to have something like this kind of generalization. So that's my previous work, that there is a non-commutative generalization of the Groveland basis and also various kinds of algorithms associated with it, such that it applies to the spectral algebra. Okay, so here is a rough description on how general the new theory is. So it considers an algebra not necessarily commutative, and it should be decreasingly finitely filtered commutative. So if it's a graded algebra, usually you only require it to be finitely filtered in each degree. It does not require a universal bound on the finiteness in each degree. Okay, so assume that it's filtered decreasingly, and the second condition is that the associated graded algebra should be commutative. After we have both, then you can apply the theorem and the new theory, Groveland basis, on it. And so the consequence of the previous slides is that we can apply this new Groveland basis to all finitely filtered commutative algebras, including primitively generated Hopf algebras, such as the spectral algebra, and also the C-motivic and R-motivic spectral algebra. So we can use the new theory to implement the program, and that's exactly what Adams is, and obtain the following. That, for example, previously I've computed the E2 page for the sphere up to internal degree 221. So in the end, we get roughly 3,000 indecomposables and 20,000 basis element as a vector space, and also 200,000 indecomposable relations, which means that it's a relation that cannot be implied by relations in lower degrees. Okay, so actually I should say that the dimension for the indecomposable relations is this number. Okay, the complete lists are given in Zenodo, the same website I upload the machine proofs to. Okay, so next I'm going to introduce.
Could I ask a question?
Okay.
There's also Grobner basis theory that people have used for Weyl algebras and some
Yes.
other sort of mildly non-commutative things. Is there a relation?
There are many kind of generalizations, and I would say that their generalization does not directly apply to this, because they usually deal with increasingly filtered commutative algebra, and then the monoid ordering would have some issue. Usually their assumptions of monoid ordering would not apply here, but with the finiteness, we can actually modify the axiom and make it work, and that's what this is.
Thanks a lot.
Okay. So for D2, the Bau's showed that we can encode secondary linear algebra in a DGA called A2, and so that we can explicitly calculate atom D2 differentials. And they have made an algorithm, computer algorithm, and they computed the D2 differentials up to stem 40. And later on, NASA found a much smaller and simpler presentation for the secondary linear algebra. So it's a much smaller DGA, so it makes the program more efficient, and this speeds up the calculation. Okay, and then in 2022, TRA generalized and implement the algorithm using the synthetic language. And so furthermore, we are not just getting D2 differentials. We are getting the synthetic homotopy for the synthetic sphere modulo lambda square. So which can be roughly thought as the Adams E3 page, including the hidden extensions. So currently, I don't have this part in my code, but I think it will be in future versions. Okay, so that's the history for the D2. Currently, my program can compute D2 differentials. So for example, right now, the machine I'm running can compute, already have D2 differentials up to internal degree beyond 200. Okay, and okay, now let me introduce the second computer program. So let me introduce the most basic data structure that the program SS uses. It organizes the spectral sequences by the following. So you consider image of D2, and it's contained in image of D3, and then it's contained in D3 cycles and D2 cycles and E2. So in other words, we want to express everything in terms of E2 elements in E2 page. So all these sets are subgroups of E2, and we consider this as a filtration of E2. And the following is an illustration of how we store things in a computer. So this is like the memory layout in the computer memory. So for example, this is the E2 page of sphere, the spectral sequence for the sphere in stem 123. So this is a typical example. Let's consider stem 123 in Adams filtration 11, and there are 5 elements. So the point is that we organize elements this way. So this is inside the image of D2, and this one is inside the image of D5. So it's in B5 here. And then this is a 6 cycle, so it's G3, and then G2, and this element is in E2. So in some sense, you can grab the first few elements, and then they will form the additive basis for G6, for example. So this choice of additive basis contain a subbasis for each subspace in this sequence. So that's how you organize the data in the computer memory, so that so you can quickly get a treatment for all these subspaces. Okay, so that's
Wenan,
what.
Sorry,
okay.
Wenan, can I ask a question? I'm sorry.
Okay.
The sound dropped out for a minute. Can you just quickly say what the basis for B2 is, then B3, then Z3?
Okay. So can you hear me right now?
Yes.
Okay, great. So B2 stands for the image of D2, and B3 stands for image of D3. And they should be all expanded as a subgroup of E2. So for example, the ER page would be GR-1 over BR-1. I think these are standard notation.
Yes, this is clear. I just mean in by degree 11, 123.
Yes. 11, 1 by degree 11, 123. Yes. So in each by degree, we have a sequence like this. So here I omitted the upper script. So in each degree, we have this. So in some sense, you can kind of think this as a matrix, but we have a lot of gradings, like a two-dimensional grading. So you can kind of think the whole data as a matrix of many matrices. So in each entry of the big matrix, there's a table like this one. And we have more than one CW complexes. So the whole thing, I mean, including all the CW spectra here, you have a graph of matrices with entries in matrices. Okay, so that's how the program organizes all the data. Okay, now let me show you some what we can do on this data. So I will model the Adam differential by an isomorphism that we consider GR minus 1 over GR to BR over BR minus 1. So that's an isomorphism. And therefore, we can define the inverse for the differential. So if you have elements in BR, then you can start to say what the DR inverse is. So there's an indeterminacy. So the value will be a coset of the group GR. So that's clear. But we often write differentials in terms of elements in the E2 page. So we usually omit the fact that the target is actually a set, not just an element. Okay, but so let's make this clear. That so if we have a DR differential of X, and for some reason we get another one. So if we get both two in two different ways, then we can make a conclusion, because when we write this differential, it means that the value for the DR differential contains an element Y1. So if we have two different answers, it means that the difference should be inside this group BR minus 1 here. Okay, so we can say the same thing for the inverse of differentials. So if we have DR inverse to G1 and also to G2, then you can claim that G1 minus G2 is inside GR. So that's how. So it means that when you make some change into to the data, then you can propagate through using generalized rule or nationality, and oftentimes you see some discrepancy. And what you do to the data is that you just add the difference to BR minus 1. And eventually, if you reach B1, there's no B1 because we start with E2 page. Then you get a contradiction, and that's how contradiction happens. If everything is correct, there should be no contradiction. But there could be a contradiction if you make incorrect assumptions. Okay, so this is how I determine the differentials. First, you just list all possible DR targets. And next, you just make assumptions for each one candidates. And then you propagate using Leibniz rule and nationality. And then you rule out enough possibilities by contradiction, so that in the end, you get a differential. So here are how we can propagate. There are many theorems to use. We can use Leibniz rule, nationality, and then we have developed the generalized Leibniz rule, and we also have generalized Mahol trick, and we also have many other structures and properties. And also we can propagate by the first method itself. So it's like a little bit recursive. We can use this method to get new differentials, and so that's how you propagate. And so for example, you can make an assumption, and then you make further assumptions to get new differentials, and eventually you get a contradiction. So that's how the programs work. So let me give you some pseudo example. So this is the most typical example. So assume that DRX has two, in the plot, you see two dots called Y1 and Y2. So in total, there are two square possibilities. You have to consider all the linear combinations. So there are 4 options, and possibly you get 3 contradictions. And in the end, the computer can determine that this is the answer. And how to get contradictions? The answer is that you just go ahead and add this differential, and use these slides. There's a rigorous way to add new information into the spectral sequence, and eventually you will reach something impossible, that two elements could disagree in E2 page already, and that's not possible. Everything in E2 should be different. I mean, two different elements in the E2 page should be different. Only E3 and E4 would have some non-trivial consequence. Okay, and let me show you another pseudo example that you can make. So there are 4 possibilities for drx, but somehow when computer adds drx, it finds no contradiction. But we really want to figure out whether the answer is option 3 or option 4. And so we should try harder. We should push the computer program to try harder to find contradictions. So for example, a typical example is if this last option is a 0 differential, then it means that x survives to the next page. And then you can start to ask, what's the dr plus 1 of x? And it could be assume that there are 4 possibilities. If you manage to find contradictions for all these 4 assumptions, then you get a contradiction for this one. So in my big table, there's so I have a table of proofs. So in the table of proofs, there's a column called depth. So you will have a line for this, and there was a column called depth. The column depth would say that it's in depth 1, and this will be in depth 2. And the way you pass the table is that you combine all these depths, and you proof. The shape of the proof looks like this. The depth is like the nested level for the itemized latex environment. Okay, and let me show you some other tricks. So for example, let's assume that there's a map from X to G, and we also have sorry, there's a mistake here. This Y should be G here. Let's assume that X maps to G. And now we can do propagation like this. So you can make 2 assumptions and you find 2 contradictions. And these 2 are the only 2 assumptions. It means that we already have drx equal to y3 or drx equal to y4. And assume that by naturality, y4 and y3 both map to W inside the spectral G. So it means that these 2 options derive the same dr differential inside G. Then the computer will be able to get that this dr should be W. So that's also a way to make to propagate. And I think so. Someone somehow I missed the slides. Okay. So I will tell you what the slide that somehow got deleted or is. So there's actually another pseudo example. So if you have a assumption that you cannot get contradiction immediately, you can actually consider a map from spectra G into spectra X. So you can pull X back to that spectra. And because you are making an assumption, that will limit the possibility for the differential of the pullback of X. So then you just enumerate all those possibilities of pullbacks of this differential. This differential could be non-trivial. So you pull back to another spectra via along some map, and then you get some very few assumptions. If they all derived contradictions, then that's also how you can negate this assumption. Okay, so that's few the examples, and I just want to show you that there are a lot of resources you can use to get contradictions because there are many maps. I made these slides 1 year ago. So currently, so here you don't see many CW complexes, but right now we have a lot of them. You can find all of them on my webpage. Okay, so next, let me introduce another an important notion called extension spectral sequence. Gordon Wang has already mentioned this. So we can consider the cofiber sequence of homotopy groups, and we filter. So the exact sequence is itself a chain complex, and then you can filter it by Adams filtration. So this is just so this is just classical stuff. So you have a filtered chain complex, then you get a spectral sequence. This spectral sequence starts with a associated gradient for this sequence, which is the E infinity pages. And then we call these differentials extensions because they encode exactly what we call hidden extensions. I mean, actually, if one does not come from the extension easily deduced by E2 pages, then we call those hidden extensions. Okay, so that's and let me tell you how the computer organize this extension data. So originally we have filtration from B2 to G2, and in the middle one is the B infinity and G infinity. But now we have the extensions, so we can insert, so we can make this filtration even finer. That you consider B0 of image of F extension, which jump filtration by 1, and then you consider the G extension kernel of length 1, and then G extension cycle of length 0, etc. And now the hidden extension is expressed this way. So in the computer memory, you still have a filtration. You have a basis of E2Y which respects this filtration, and then you organize this DRF in this sense. You get, and there's a special case, there's an edge case here. So actually the 0F is G infinity over G0, which happens here. And the target would be B0 over B infinity. So it happens here. So the conclusion is that if somehow you get two different extensions, then what you have is that you add the difference of the discrepancy to the images of the shorter extensions. So if R equals 0, so that's the edge case. If you get two different elements on the E0 page, then it means that the difference should sit inside the Adams boundaries. Okay, so this is actually very powerful. That if we consider an element in the Adams spectral sequence, first you ask what's the D2 differential. If it's 0, then you ask what's the D3 differential. If sometimes for degree reason we get a permanent cycle, and then you start to ask what's the G extension. And sometimes for degree reason you can go all the way down to Adams boundaries. So I have examples that if you just consider a cofiber sequence, then for degree reason, you immediately get an Adams boundary. And that's how you can get a very long Adams differential, because just for degree reason, you know something must be cured by Adams differential. If there's only one chance, then that's the only one. Okay, so the program will also support homotopy data. So currently, the feature is not complete yet, and I wanted to support the actual homotopy data, and it will interact with Adams differentials and also the extensions, but the feature is not complete yet. Okay, let me tell. Right now, I'm going to introduce how to use the computer program. So on the Zenodo, where I uploaded the machine proofs of all the Adams differentials and extensions here. I also uploaded other stuff. For example, I also uploaded the executable computer program. It's inside the programs.zip. I recommend you to download and play with it. So inside there is a demo inside it, and you can play with it. And I'm going to show you the demo right now. So here's how you use the Adams. So you have to use a terminal. There's a terminal both on Windows and MacBook. You just search for terminal, and it's already built into the system. You can open it up, and then there's a slightly non-trivial thing you have to learn, that you have to learn how to navigate your terminal to a forwarder. And you can Google it, and you just have to open the terminal and then change your current location to the folder where the Adams program is in, and that's it. And then you can start to do what I'm doing right now. So you can run this command. You just type in this command, and you just press enter. Then you do the this thing. So assume that I is a ring spectra. Then you use this command. You can use this command to compute the minimal resolution, and you can use this command to compute the algebraic structure on the E2 page. And then you get two very large data, one for the resolution, the other one for the product structure. But in the end, we just want the Adams E2 page. We don't want A modules. We just want a vector space, the E2 page, which should be small. Then you can export it. Then in the end, the result, you get a file named with a ring R and then Adams ss.db. That will be the input for the program SS. So Adams is just like the upstream program. You produce a lot of output, the E2 data, which can be further processed by the SS program. So now here there are two additional things. You can run these additional two programs to compute the D2 differentials. So you just run these five program. I actually omit a thing. There is a the last argument of all this is the range you want to compute. So you should put resolution R and 100. It means that you compute the minimal resolution up to 100. Okay, I will show you on screen. So let me show you another doc file that if you have a module X over R, then you just for the resolution, the command is the same. For the product structure, you have to tell the computer what X is over. So you have to type in two arguments, one for module and then follow with the ring R. So for example, X could be TMF smash C cofiber of 2, then R could be TMF. Then the program will compute the product, the module structure. So sorry, there's a typo here. This should be a module structure of X over XR. Sorry for the typo. And then you can export. So for exportation, you also need to specify both the module and R, and then you produce a file called X underscore Adams SS. And okay, and you can also export the D2 data. So this command, the exportation for D2 data, actually do not generate a new file. You'll be merged into this database file. So you can kind of think database as an Excel file with many sheets. So there are many tables inside the same file, and this D2 would just add it would just add another column into certain table and tell you what the D2 is. Okay, so that's what's behind the scene. And there's also two commands for computing the maps. You have maps from if you have a map from X to Y, and running this command will give you the chain map between the two resolutions. And you can also export the map, and you get a very small file, just specifying how the E2 map to the other E2. Okay, so let me show you on screen. So if you if you download the program from Zenodo and decompress it, you get a folder like this. There I've provided programs both for Windows users and Mac users, and so you can run the program without trouble, unless you are using Linux machine. But I haven't produced one for that. Okay, so let's try to compute the resolution of S0. Let's compute it up to 80. Okay, so right now it's done. I have resolution up to 80, and here you see a file called. So let me zoom in. So now you see a file called S0 Adams resolution.db. Now I can compute the product. It takes longer. Then you get a file called Adams resolution product, and then I can export. So now you get a new file called S0 atoms spectral sequence.db, and that will be the data, the input for the SS program. Okay, now let's try out for modules. Let's use Kervaire 2 resolution C2. Okay, that's fast. And then let's try the module structure. So you just type in product module and then the module and the ring. Okay, and then you produce the module structure. Again, and now you just export the module. And you also have to be careful. You have to specify 2 arguments, the module and ring at the same time, so that it can export. So this command will actually use the exported file for H0. So you have to export it for the sphere first before you export for the modules. Okay, now it's done. And I'm not going to repeat for other fiber of Hopf elements. I'm just going to copy and paste into the terminal, and let's just wait for a few seconds so we can compute all of them. So in today's demo, I'm going to compute 5 CW spectra. One is sphere, and the other 4 is the cofiber of Hopf elements, namely cofiber of 2, cofiber of eta, cofiber of nu, and cofiber of sigma. Okay, now we are done. So here on the left-hand side, you have cofiber of eta atoms SS, cofiber of nu atoms SS, cofiber of sigma atoms SS, and that's what we want. Now let's go ahead and compute 4 maps. So let's compute the map between chain complexes. So the order is the same as the order of maps. So the map is from C2 to the top cell. So this should be actually the suspension of H0, but for some reason you don't have to input the suspension. You just use the relevant module itself. So the suspension will not show up in the command. So there's no ambiguity because in a definition file, I only defined one map from C2 to a certain suspension of H0. So there's no ambiguity. The computer will just go ahead and select this map and compute the map between chain complexes. And this is fast. And let's export. Okay, we are done. And now let's just copy and paste, and let's compute the other 3 maps. Oh, sorry. Okay, that's fine. Okay, so the exported file is named like this. There's a file called map atoms spectral sequence from C2 __ S naught. So that's the top cell map for C2, and this is top cell map for C eta. So these are the inputs. So the other 4 is the chain maps. These are huge files if you compute things up to a very high stem. But if you exported the file, you just preserve the E2 page information. That will be very small. Okay. So next, so we have all the atoms E2 data available. Now let's just go ahead and let's move to the next program called SS. You take all this E2 data as input and deduce a lot of atoms differentials for you. So this is how it works. So let me show you the folder. Okay, sorry. Sorry. Okay. Okay, so you can see that in this folder, there's a folder called demo. So so right now your program is in this folder, and inside this folder, there's another folder called demo, and that is where you place the category. I mean, place the collection of CW complexes, and we have already computed all this, get all these atoms SS data. Let's just move in to this folder. So there's a neat command called copy all this file containing atoms S, containing atom SS, and let's copy it to the folder demo. Let's go ahead. And now in this demo folder, you can see all the atoms SS are copied to here. And there is a configuration file. You should place it here. You should tell the atoms, the SS program, what gadgets are you considering. So here I've already edited this configuration file. I'm telling the computer that I'm considering one ring. So that's S0, and the file name is this. And I also have 4 modules over S0. You should also tell SS what the module is over. What ring it's over. And there are 4 maps. These are the top cell maps. The reason some people may ask, what about the bottom cell maps? The bottom cell map is already encoded in the module structure itself, because the bottom cell is a permanent cycle. So you don't have to add those maps. It's already encoded in the multiplicative structure. You just have to add top cell maps, and then you have to give some maps that's already encoded by multiplication. You don't have to compute this map, but somehow when I want to specify cofiber sequences, I need a way to tell the computer what the 3 maps is, what the 3 maps are, and some maps are just maps you don't compute. It's already in the product structure. So there's an entry called maps v2. It just tell the computer how to get this map from the multiplicative structure. For example, you just multiply this element and you get this map, and that's so for example, this is from sphere to sphere by 2, and so this is where you tell the computer that inside the cofiber sequence, the 3 maps are a bottom cell map and a top cell map and sphere to sphere by 2. Okay, so this is a project file that tells the program what your category is. Okay, now everything is ready. All the paths, all the files exist in the folder. So the SS program will be able to find those files and construct this category. And now we can do a lot of things automatically. Let me show you. So the first one, you have to initialize the demo. Sorry, I think I made a typo here. There should be no underscore SS here. You should just use reset. You can reset the category demo. Before you do anything, you should always reset. So let's type in atoms SS reset demo. And you have to confirm. Okay. So what the computer does is that it's adding. So in the very beginning, you see a lot of outputs that start with D2. It means that the SS program is absorbing the D2 information we've provided it. And so you see this message. It means that the computer is adding all these D2 differentials we already have one by one. And then sometimes you see some line by NAT, started with NAT. It means that the computer is considering nationality. So you have a D2 in cofiber of new, then automatically by nationality you get a D2 differential in sphere. So there are details thing on what the computer is doing. So, and then if your line start with degree, it means that you get this differential for degree reason. If there are no dots above these points, then it cannot hit anything. Then just for degree reason, this happens. So the computer is logging all this information, and then you get something interesting that's called extensions. So these are extensions. So let me explain what this is. So usually you start with the cofiber sequence name with a colon and then a number. So this number could be 0 or 1 or 2. If this is 0, it means that you are considering a map from S0 to C2. And if this number is 1, it means that you are considering a map from C2 to the top cell. And if this number is 2, it means that you are considering the map from this element to the very first element. Basically, it's the boundary map. So this is specifying what extension you are using now. So actually, there's what I said is not completely true. Now sometimes you will see that the differential is written backwards. So you are actually considering the inverse of an extension. Then it means that this 0 sits inside S0, and by inverse of extension, it means that you are considering map from the previous one. So here you are actually considering the connecting the boundary map extension. Okay, so that's what the computer is doing. Now let's plot. There's a plot command called plot spectral sequence, and together, and then with the category called demo, and let's plot. Okay, then what's happening is in the folder I've given you, there's a subfolder called web pages, and these are web pages you can open locally. So after you run these commands, all the plots will be written to the subfolder inside the folder web pages, and you can open your files, and then you can find a file called plot.html. So that's just a web page file. You can just double click. It works both on Mac and Windows system. You just open it, and the system would open it in your browser, and then you can find this plot. So for example, we computed everything up to 80 in total degree. So you see that this plot is up to 80, and you get all these differentials. And you see that when the program initialized this category, it already deduced a lot of differentials just for degree reason. So we know that these elements are permanent cycles just for degree reason. So the computer is not producing anything non-trivial. It just applies the for degree reason arguments and then the Leibniz rule. So for example, we know that this is a permanent cycle. It cannot support D2 differential just because it knows that the previous one supported D3 differential. So this one should also support D3 differential. So it looks like it could hit here, but it actually has other decompositions, and you can actually get past this point, and it's survive. So the computer can when you initialize the category, you can already make sure that everything is non-trivial. I mean, everything is at the status that you have to consider the non-trivial thing. Okay, so that's the plot. Let me switch back to the slides. Okay, now here is the interesting command you can play with. It's called deduce auto, and then follow with the category. So this would deduce the Adams differentials and extensions for the category demo. So let's do it. Let me show you. Let's type the program SS, and then let's type deduce, and then let's type the next subcommand called auto, and then demo. Okay, and now you can just watch the computer program to deduce all the differentials. And now, if you run it again, you see that the computer can no longer get new differentials. So, okay, so remember that I can push the computer harder to get new differentials. If the computer have difficulty getting contradiction, you can push it harder. So there's a way to put flags. There are many flags. Here is one example. So the 0 here means that the computer would try something like this. If a differential is 0 and somehow it cannot get the contradiction, then if you provide a flag to the program, then the program would try harder to find a contradiction. You consider the next target of the differential, and if it gets a contradiction, then boom, you get the answer. If there's a one that you cannot get contradiction, the computer will just give up and say that, oh, this is inconclusive. Okay, Now let's try harder. Let's provide a flag called 0, and you see that we are getting new differentials, but not much. Okay, so but let's try the general Leibniz rule. There's a command for generalized Leibniz rule that Guozhen talked about yesterday. And we can apply it. You can see that the command runs very fast. So for example, Guozhen yesterday talked about the D3 differential here from the D2 of H5 in STEM 31 in filtration 1. And you see that quickly that's the first example for generalized Leibniz rule. And you see that you get this. And you can run all the commands over and over until the computer can no longer find new differentials. So you see that after we get new differentials from the generalized Leibniz rule, then we can keep getting new differentials by Leibniz rule and nationality again. And then you can switch back to synthetic. Let's try, after we get this new differential, can we more effectively apply the synthetic method again? I mean, it's the generalized Leibniz rule and also the generalized Mahal trick. Let's do it again. And it turns out that there are only Mahal trick that can obtain new things. We get no new Adams differential, but we do get a lot of extensions. So that's from the generalized Mahal trick. So let's go back. Okay, we are almost done. The computer is dry out. We get no new stuff. Now let's plot to see what it is. Okay, after we plot, you can just rephrase the web page. You'll be updated to the new status. So you see that we get D3 differentials. Actually, we can also get D4 differentials. The machine. So these are all obtained by the machine automatically using the Adams differentials and extensions. Okay, and that's it. Because we don't compute very far, we only compute up to 80. So that's all the computer can get by the current features. Okay, I have 8 minutes left. Let's go back to the slides. Okay, let me tell you what I've been doing beyond the Kervaire, beyond solving the Kervaire invariant problem. So actually, right now you see that I'm having a lot of Adams, CW complexes. Some people may ask, for example, when I compute the Adams E2 page, people may ask, how can I add a new CW complex yourself? The answer is that you can do it. There's a configuration file for you to define new CW complexes in a file, and it's very I think it's self-explanatory. You can just mimic what I've written for modules I've already computed, and you can just add one on your own if that CW complexes exist. Okay, so let me explain a little bit on how to define new new CW complexes. So for example, for RP14, we have 4 cells in dimension 1, 2, 3, 4, and this is a choice for the indecomposables. So later on, you can use the indecomposables to define maps. So since these 2 cells generate the whole cohomology, there's no need to specify the map for other cells, right? So here you make a choice for indecomposable. Later on, you can just specify where the cohomology go, and you can define maps. So that's for maps. Here you have to define. We are defining for cohomology, a single cohomology. So here are the power operations. You can say that there is a square 1 operation from cell 1 and cell 2, and there is a square 2 operation from 2 cell to 4 cell, and then a square 1 from 3 cell to 4 cell, and that's it. And that's how you edit how you add a cohomology. And so the principle is that the difference between the between the dimension should be a power of 2, because we all know that the Stirner algebra is generated by square 2 to a power. So you only have to specify how those square 2 to a power acts on this cohomology. And you may ask, what happens if there are more than one element, more than one cells in a dimension? Then here I don't have that example. Then yeah, I will give more instructions later on the Zenodo repo that there's a way to consider even more complicated cohomology. So yeah, so you can just add. So my point is that all this work are done by me manually. So so you see there are a lot of CW complexes. So I have to manually add them one by one. So that's a lot of like logistic work. So in the future, I want the spectral sequence, the SS program to compute homotopy groups, and then it should construct the CW spectra itself. So for example, if you start with the sphere, then you see that there are 4 Hopf elements, and then there should be 4 interesting cofibers, because they live in filtration 1. So you can get interesting cofibers such that you can get non-trivial Stirner operations in a cohomology already. So they are considered interesting CW spectra. And then the SS program will notify the Adams program to compute the cohomology for this new CW spectra. And then the CW spectra after the Adams spectral sequence finish the computation, it should notify the SS it should say that, oh, I got a new CW spectra, and so the SS should consider it. And now SS can compute the homotopy of the new CW spectra, and this goes over and over. Now you have 2 cell complex, and you can compute the homotopy group of 2 cell complex, and you can add 1 more cell to it, and this goes on. I want this to be automatic. And then next, what I want to do is I want to use Leibniz rule of the following form. We are very lucky that in the category of finite CW spectra, that we can form dual, we can form smash product, and they are all finite CW spectra. And so we can consider things like this. So it means that we are literally computing the stable homotopy category itself. We are considering maps between modules, and they just compute all home sets and compositions, and we can do that. But we are doing it. Okay, so then we can actually compute the homotopy data. So there will be a choice system for the homotopy elements. So the computer will be aware for the indeterminacy always. There's a sophisticated managed system for choices for homotopy elements. It's not feature complete yet, but it will be done. And next, we can also add the R-motivic and C-motivic data. Remember that we can use the C-motivic and R-motivic. We can use the Adams program, the global basis standardization for C-motivic and R-motivic Stirner algebra. Okay, so I think that's roughly my the end for my first talk.